In this video, we're going to review a little bit about kinetic energy, and work and the work energy theorem, and also then introduce the new concept of potential energy, pretty much just stepping forward and a little more into energy from the last chapter. And something to think about in this first part of the chapter is it takes work to climb a mountain on a bike. You might remember that question from the test about climbing a mountain and what gear ratios we need. So how does this work compare to the work we get back out when we descend? So take a moment, pause. If you need to, think about what your answer to this would be, and then we'll start up again in a second. So hopefully one of the things you realize is that if this were an ideal situation with an ideal machine, the work that we used to climb the mountain, which would come from our own energy of our bodies, we would get back when we came back out, so that work would be turned back into kinetic energy coming back down the other side. So whatever work we put in, we would get back out. However, because it would take a bunch of work to go up the mountain that we would also lose because of friction, there's friction between tires and the ground, there's friction between wheels and hubs, there's friction between chains and parts of the drive system, and then on the way back down, there's still going to be friction. Now we're going to have air resistance playing a greater part, probably coming back down. And so the work we get out will always be less than what we get in. And we did those problems with efficiency in the last chapter, so we have some idea about that. All right, so as I said, our objectives here are to use and calculate kinetic energy, work, and potential energy together. So just to review the work energy theorem, this says that the work done on an object goes into increasing this kinetic energy and vice versa, so it takes work to decrease the kinetic energy of an object also. So when you speed up or slow down, you are doing so by either doing work or having work done on the object. And kinetic energy is the energy something has because it's moving, and it's calculated with this 1/2 mv squared. So kinetic energy is dependent on the mass, but also doubly dependent on the velocity because we square that. Okay, so let's make this connection now to potential energy. We know that the definition of work is F dot delta D, and if we assume that the force and the distance are in the same direction, then we can just multiply those. But what if we're going to lift an object straight up in the air? Then the F would be the weight of the object. We're assuming we're going to lift it straight up and at constant velocity. And Fw is equal to mg. We learned that way back when. So plugging that in, we would have that the work done to lift that object up would be mg, which would be the force from up here, times delta D. Or since we're talking about lifting, maybe height's better than D for distance, so mg delta H. We would call that quantity, this work now, mg delta H, the gravitational potential energy. There's different kinds of potential energy. This one's because of gravity. It's got the G, the gravitational constant in there. And so if we wanted to find potential energy simply, we would say potential energy is mg times h. Now there's going to be some tricky things about potential energy, so in the second part of the video, we're going to pick up on that and go forward.